Hello, everybody, or just Justin, who's live today. Yes, and yes, Winnie. I think she was here last time, I remember. Thank you for coming. Today, I'm going to be working on the PWM module of the TIVA-C, and I think in this presentation, just a brief introduction, really, what I can do outside of class. So yeah, pulse width modulation, PWM, there you go. So what is PWM? PWM is just a term to describe a type of digital signal, which if you look at the name, it literally is just a pulse that's being repeatedly sent, right? So if you look, you can think of a sine wave, but in terms of engineering, we can't really get to sine waves. The closest we can is like a square wave, and then we modulate that a little bit, right? And it's used in a variety of applications. Common examples would be your brightness, right, and dimming of. Most of the time, if it's not the screen one, you're using motor controls. Like, for example, Dr. Lay's embedded class, we use some motor control there. So it is a handy tool. Also, it's very advanced. And oh, it's bright in here. Over here is a duty cycle. So I think let me explain what a duty cycle really is. It's how much how much is on and off time of that signal, right? So if you look at the top, it's 10%. The reason it is 10% is because based on its period, it's on for 10% of that time. So if we go from here to here, right? That's one full cycle. You can see that it's only on for, like, let's say 10%, and 90% is off. So you go off of what's on and not off. Over here is 30%, 70% is off, right? Here 50, this is your perfect square wave, and 90% is off. So if you think about in terms of brightness here, what over here would be like basically what is similar to your screen, right? It's on the whole time. And the lower you go, and also, by the way, because it's a signal, E equals MC squared stuff, basically a wave can both also transmit energy. I think you'll learn in some of your other classes. And because the more it's on, the more energy, the more brighter it is, really. Yep, there you go. And now let's talk about on the TIVA-C itself. Basically, anything I say here is all from the data sheet. I mean, I only pick like small parts from the data sheet here. I might recommend reading it. Data sheet and everything else, it's on the GitHub for this workshop. Just go to the resources folder and you'll find a data sheet PDF. You'll find a user guide PDF on the TIVA-C, and then also an API library, peripheral library on the TIVA-C itself also. So back to the TIVA-C. So we have two PWM modules, right? And each module has 4 generators. And each of the 4 generators gives you 2 outputs. So total you have 16 PWM outputs. And these PWM outputs can be independent of each other. The reason why is because the generators can be independent of each other, or they can be synchronized together. When you do motor servo, you do want to have them synchronized because the wheels got to move in a certain pace, right? If you don't do that, then one wheel might be going faster than the other. So that's something that's more advanced than what we'll cover here. And right here is just the PWM module diagram. And I think what you want to look at is what I just said earlier, how there's 4 generators, right? So this is 1. They only show you 1 because there's 2 of the same thing. So 4 generators, and at the end you have 2 outputs here: 0, 1, 2, 3, 4, 5, 6, 7. For this example, we're using 4, 5, 6, and 7 output numbers, and the reason why it's because it connects to a certain pin we'll talk about. And here we'll show you the pins. So each one of the outputs, it corresponds to a certain pin number. So let's say you configure module 0. But if you don't connect it to the right pin, you're not going to see it. Right. And again, we will be using module 1 generator, and we will go from PWM 5 to 7. We use 4 too, but we can use 4 as well. It's just with the 4, you have to connect an external something like a signal detector, etc. So 1, 2, and 3, sorry, 5, 6, and 7, they're also happen to they're in port F, and port F also has a LED, so you can see it better, right? This is important because, well, if a lot of people were in the class, I was gonna ask them to code this, but it's only me, so I'll do it later. Anyway, demo time. So I will stop the share right now. Matthew will do something special, and then we'll just go towards coding it.
What class?
So Matthew, what else supposed to do? Because I gotta code.
You're fine. Just give me 1 second.
Okay.
But what class would we use this ID for?
Hey, which one is the one Dr. Lake teaches the first time around? I forget. Like, I know the name is embedded or something. No, I mean he's talking about the class. It's embedded what? I forget.
Oh, so it's microcontrollers.
Well, embedded microcontrollers. There you go.
Microcontrollers.
Yeah. And then that's the required one if you're a computer engineer or electrical engineering.
Right.
And if you take your, oh my God, was it? Is it? What do you call it? Is it optional or the other? I forget. Like, you know, those 3 classes for computer engineers that you have to take, but you can choose which one. I forget what is the term? Electives. Yeah. If you choose an elective with Dr. Lay, then he uses Keel and stuff. I chose ADD, so I use FPGA now, which is cooler, way cooler.
So now you can see your TIVA.
Okay. All right. So let me share my screen.
Oh, I gotta share it.
Yeah.
This problem with Zoom, it's like I have to let you share.
Yeah.
You know, no, you're doing code, right?
Right. So I mean, unless you're okay with me not showing the code.
That's okay. We just screen sharing.
So I don't know essentially if you saw it earlier that he was see, but he was blinking blue. That's pretty much what we're gonna do. But I'll start with red first. Okay, let's go here. So here I already have a project set up. So if you're doing this at home or at a later time, and when you create a brand new project, please do make sure that you have the correct path stuff. So this is the folder we added last time. And in the ARM linker file search path, we had added the library, right? This one, you need that. And so each time you make a project, it doesn't add it by itself, which is stupid, but so you have to go and do it yourself. And before I came here, I also sort of had like the potential driver list, just separated it out so that I wouldn't waste a lot of time coding it. But I will explain, or rather just talk about what each one is, sort of. Here you go. What is that? Let me try to build it real quick.
Wait, is this thing C or C++?
It's C++.
Oh.
Compilation for one result. Yeah. Okay, looks like you can't copy paste. It's gonna copy paste some special symbols. So all right, let me just type this out. Yeah, okay. Well, that's fun. Okay, then we'll just do it the old school way. I'll just type out each individual one. So let me just do int main here real quick. Okay. So that's just to make it a code. Now we need to basically include the libraries first because it is C, sort of picky, and also because it's Code Composer Studio and it doesn't like not having libraries, right? All right, so I have it next to me here. An example that I made out. I'll just type it. As the first, we will include some of the standard C libraries here. Okay, so include. And so the reason these are in brackets is because this is in a certain directory. So it's an absolute directory. So the computer sort of knows where to look for. What it's doing that two thing. I don't know if that's going to cause issues. Okay, it doesn't cause. All right. That's fine. Don't worry about the red stuff on the bottom. It doesn't matter. And I include in this library that I'm adding stdint. This one has these things like, I'm going to type this, but I just want to make sure I'm typing the correct unit 32 data types. So if you don't include this right here, you cannot have these variables. And what this is just means unsigned integer 32-bit, right? You have to declare that in Code Composer Studio, but if you were doing it in your like Bloodshot C/C++, like Dr. Hebert uses, you don't have to. So it just Code Composer Studio doesn't do that. And you have to also include a library for bool. The reason why is because when I was making this and debugging, I found out that, hey, some of these libraries did include bool, so then it was crashing. All right, so now these are the absolute path ones. So now we'll go into the relative ones. All right. So include inc/hw memmap.h. So this library, this library defines the base port addresses for the GPIO pins. So if I don't do that, I can't use the API functions, or the API functions will not be able to do it. And again, I think I didn't explain it earlier. The reason why we're doing it with a lot of includes, because if you're in C, if you're using this in Q, or if you use assembly and whatnot, most of the time you only need to include like the board. But the reason I'm including all of these is because I'm using API functions just to talk to the board, so that we from our end don't really have to worry about the individual registers. When you use it in Q, you have to sort of worry about the individual registers. So this is like a layer off of embedded programming. Also, it's faster. It's very much faster. And then now this one include /h hardware. HW stands for hardware, GPIO.h. And this one includes a set of values required to unlock specific function pins. And again, most of the time, the microprocessor locks the GPIO pin, so you have to unlock it in a need basis. Okay, these two ones, it's gonna be sort of slow, sorry, but I tried copy pasting, didn't work. Driver lib /GPIO.h. So this include library, it includes GPIO functional values and required APIs, right? API functions. And again, all of these functions that I'm going to be using, their documentation is under the resources folder on GitHub. And this one include driver lib /pinmap.h. So this one includes API functions based on the pins for most TI microcontrollers, including the one we're using. So again, some of them, it doesn't have support for it, but include driver lib /pwm.h. So driver lib just means driver library. pwm.h is the module we're using today. So it's driver library for the PWM module. And include driver library /sysctl.h. So this is sysctl stands for system control. So we're including driver library for the system control. So it lets you talk to the board itself. And lastly, we have include inc/hardware types.h. This one's for required H hardware register macro that we're going to be using. Okay, now we got to check if everything is fine. So return 0. So let me build this. You should do this often whenever you're coding. Also, just especially in here, so that you do catch the errors beforehand. So, okay, cool. No errors. All right. Now we will go into configuring. So first, we have also every one of these API functions we're using. All of the words, they're like the string values we use is translated into the unit 32_t, because that's just required for the API signals, right? And it really is just a 32-bit value, which when the preprocessor translates into machine language, it just becomes the 1s and 0s. There you go. I mean, I didn't know why I felt the need to explain that, but there you are. Most of you would know. Anyway, all right. So right now we're going to enable GPIO for port F. That's the port we're using. So it's, you go SYS, CTL, CTL, PERI, PG. So this means system control peripheral enable. Peripheral because it's outside of the thing. This is in all caps. System control perif, PRPH, GPIO, F. So if you're using any other port, you would just put like, this is the part that would be different, right? Okay. And now, after that, we also have to enable the PWM. The one we're using is PWM1. Control plus. Did it do it? I think we had this issue last time, and yeah.
Control and scroll.
Control.
Oh. Nope, fine. Okay.
Okay, sorry. Yeah, no, I think it's, I don't know. I just
Wait, actually, couldn't you just like move the window from the left, like
like, no, I think it just messes a little bit.
no.
Sorry, let's just move on.
You still see it, it's just,
Yeah, I know.
it's all good.
Okay, I think next time we'll figure out. And then this one, it's the same function here, just different value for the PWM. So we'll go, let's copy that, paste it. Okay, so in here we go. So you can copy this entire thing. Right. So this will be different here. This will be PWM1. So again, as I explained, there's two PWM generators. Actually, no, two PWM blocks, right? PWM0 and PWM1. We're using PWM1 so that we can use generator 2 and 3. Okay. So after that, cool. Now we have to set the clock speed. Not the clock speed, the clock for the PWM module. It doesn't have one by itself. And this one basically determines how fast it counts the ticks, I believe. So the function for that is SYS CTL PWM clock set. So all of these API functions, what it replaces, it's the need for you to talk to an individual register. And for so if you go follow the data sheet, what you'll find is that it will talk about an individual register, right? Which is what you would normally do if you were, using Kill to use assembly language, or even just the C version of that. You just talk to the register step by step. So if you follow the data sheet, you can also just code it. It just won't be with API functions. It will also give you a better understanding of what is actually happening, really. So in here, the clock value I'm about to give you is the default clock speed of the processor on the board divided by a certain value. So CTL underscore PWM PIV underscore 64. So what this does is it divides the default clock, which I believe is 80 megahertz here, by 64, which is the smallest you can give. It comes out to about 1.5 megahertz tick speed, right? Like the only other clock value that you can actually see would be 16. Divide this by 16. If you divide by 1 and 4, it's just a little bit too fast. Okay. So now this is unlocking the port F values. Yeah, unlocking port F for alternate functions here. So because we're using PWM, we have to sort of unlock it for alternate. Usually, if you're just writing it for LED values, you don't have to. But because we're using a PWM, you do have to alternate this. HWREG, which just means hardware register, really. GPIO underscore port F underscore base. That's the base. Plus PIO underscore O underscore lock. Right. Equals GPIO lock key. Okay. So this macro we're using is from this library, right? HWREG, GPIO. Also, if you follow the code, which all of this what I'm writing, most of it, like this exact one I have next to me is also already on GitHub. I'm seeing there are other comments which you can read, and like the articles I used to write this code at home. The only thing you won't have is the code I had for a group project for a similar class a year ago, because that would be academic dishonesty. So I don't have that. So this method of writing right here is sort of similar to how you would write in Kill, right? And because we're talking to a register, that's why you would write it this way. Okay, here we are. So these functions enable the access to GPIO pins of port F. Without unlocking them, only default access to pins would be available. So that's why we need to unlock them for PWM. So now we're configuring pins, right? Of port F. So we said we're going to be using pins 1 through 4, which translates to PW port F1, port F2, port F3. Okay, because each port F has four ports we're allowed to use on them. Okay. So we go GPIO. So the API call for that is GPIO pin configure GPIO _ PF 0 _ M1 PWM 4. And so the reason this is PWM 4 is because if you look here, oh, I guess I'm only sharing you the coding screen, but if you go to the PowerPoint or even data sheet, oh, I guess actually you can see this. If you go there, you can see that PWM 4 right here, right? So, and we're using that essentially. So for 4 corresponds to. So let me just complete this and then I'll it is going 6 and 7, except we're not going to be using 4 anymore, because 4 is PF0 and PF0 it's not visible unless you plug something to it, which we're not doing. So PWM, right? So let's see. So pin 5 is PF1, pin 6 is PF2, pin 7 is PF3. And you could guess pin 4 is PF0. So, okay. Now let me stop and check if everything is okay. Everything is not okay. Let's see. Good thing we have it here. Let's see. What did I miss?
It's not initializing.
Line 34 cheaper configure P. This is undefined. Really? Yeah, I think I missed a driver. Hold on. Let me just double check. I think so. I'm checking. Map GPIO.h GPIO. I think did I miss that? No, I didn't miss that. Left TRIV. No, I don't think I'm missing a type, so I don't know why. What? Welcome to coding. What? GPIO port F0. Oh, it's I think I'm using PF. No, that's right. Yeah, spell it right. I have to check the spelling now. GPIO PIN. Right, let me try to do one at a time. Okay, hold on. Right, now the error should only be for one of them. Identifier, that is undefined, right? This value is undefined. Okay, hold on. So now this is where having previous code comes into play. Which we did. All right, so let me open that with here.
Oh, no, you've shown it, Neil. Oh, what? You showed it.
So this is the one I made. Yes. I'm trying to see what did I miss. It should be 1, 2, 3. Actually, hold on. Let me just. I'm going to overwrite this. Hopes that it works. Because if not, I'll have to copy the previous code. Okay. Well. Really confused. Why is that not working? Hold on. Yeah, I'm not spelling that correct.
Wouldn't be a one shot.
Yeah, I don't. I think I'm just not spelling things right. Hold on. Let me just. Oops. Yeah, I think I just didn't spell it right. That's funny. I just didn't spell it right. What? Oh, wait. It doesn't let me. I think it doesn't let me skip. So I can't use 5 before I do 4. It looks like. Yeah, that was the issue.
Wait, why couldn't you copy it and paste it over again?
I mean, I can do that. It's just I don't. That's where's the fun in that, right? I think what I just because when I was doing this at home, I did it sequentially. So it looks like I can't just skip 4. Because if I skip 4, it won't let me, and I don't know why. So that's something you should ask Dr. Levy when you get there. But now, really, that is interesting. Because it's saying I can't use 5. Why can't I use 5? That's funny. Oh, I think I know why. Wait, hold on. That's because it's the wrong value. Okay, sorry. Apologies. I think earlier when I was typing, you can see here, these values, they have to also change. I wasn't changing them. So here we are. So let me Control Z this real quick. Hold on, all of this. I will keep that. Figured out the issue. Because I was using M5 here, I also have to change this. Because 4 belongs to P.PF0. 5 belongs to PF1, even though I set it here, right? And here, I forgot to actually change it on the screen. So that's one of the reasons why it wasn't working. So let me go back now and then change it. So this will be PDF2, PF3. And if you look, it will now build. There we are. So yeah, little details matter because each one talks to a different register when it translates. In any case, so now if we have configured GPIO pins, now we have to configure these pins again to PWM, right? So the API call for that is GPIO pin type PWM. Okay. So it takes in the base value, then it takes in the ports. So the base value is GPIO underscore port F underscore base. And then again, each one of these is like a 32-bit value that gets translated whenever you compile. And so then now, since we're using GPIO pin 1s, so basically all of these pins, pin 1, 2, and 3. We're not using 0 here. So here you go, GPIO pin 1. Let me copy that. pin 2 and pin 3. Yeah. And instead of commas, there should be a little pipe bar. It's an or thing. Yep, that's it. Let's go to end, check if everything is fine. All right, we're good to move forward. Let me, this should go here. Configuring. All right, so now we have to actually configure the PWM module itself now. And the way it works is that you have to configure the generators. Generators first. And the mode of counting, right? So let me first do that. And the API call for that is PWM gen configure PWM1 underscore base. Because that is the base of the generator block. PWM generator 2. The generator 2 has, okay, what is that sound? Sounds like some ice cream. Generator 2 has 0 and 1 and pin 4 and 5, and generator 3 has 6 and 7. Okay, so from here, but we're not using 4, so it doesn't really matter, but we still have to configure generator 2. PWM gen mode down. So this one here, this is for the counter that's inside the PWM. So like when you go down to the nitty-gritty of things, the way the pulses are generated is that there's a value to count towards, and each time the value is reached or emptied or whatever, it's just there's a signal that shoots. And the gen mode, which I spelled wrong here, this one creates a sawtooth wave. Usually that's probably what you're gonna use most often. So by itself. And and the way it does that is explained on the data sheet. And there's another option, is called up-down count, which it creates a triangular wave, and it's not necessary. It's not used, at least we didn't use. I didn't use it for any of the classes, but you can use it. I mean, there's nothing stopping you from using it. And then PWM gen mode no sync. So there is no, it's an independent. It stops it from synchronizing to the clock before it sends an output. So it sends an output immediately when you have this. These are optional values here. This is sort of required. And the same thing, I have to copy, we paste it. Only thing I have to change here is the generator number, which is 3. Okay, cool. I don't think I need to write comments on this one, just because the comments, it's got like comments like these are there already on the GitHub folder. So you should be able to understand that. And I did just explain what these things were. I will say just talking and coding at the same time is pretty difficult. I haven't done since. Yeah. Cool. So now also, because now we're going to be setting up the clock suite here. I don't know how true this is, but whenever I Googled how many clock ticks is a second, I found 1 million ticks is a second. Okay. So we're going to be using it, because anything less, it's very hard to see. So now we have to set the period for the PWM module, right? Setting period. And if you dig through the API function list, this PWM, let me type this period set. It actually sets the amount of ticks between each modulation. That's which sort of is the period, I guess makes sense, because the modulation, I believe, is being defined as the time when the signal is high. So the longer the period here, and this is how you create a duty cycle. Now, when you do this with the actual register values, you're actually creating a load value, and then you modulate there. But over here, you get to sort of define your own period. And it takes in the base value, the generator, and the amount that you want the ticks to be, okay? So the base value here is PWM1 base. Okay, then you have PWM gen underscore 2 and 10 million. You got 10, 100,000, 10,000, 100,000, million, 10 million. All right, that's it. Now I'm gonna copy this. Go to end. And all I have to do is separate the generator, and there you go. It sets the period. So the period is being set at 10 million ticks. And I may be wrong here, but the way it sort of works is I think the ticks is being counted by this clock value here. All right. So if you make this smaller, let me just take it counts faster. This is the smallest I can make it so that it's sort of visible on the actual TIVA-C. Right now, the TIVA-C, it would be blinking. It just before I started this, I turned it off so that it doesn't mess up with the example here. There's an error. Let's see, undefined. Okay, Gen 2 and 3 is undefined here. No, here. Oh, 46 and 47, right? Configure, actually, this is a different example. Hold on. Yeah, I probably typed something wrong again. Happens. PW1 underscore base, PWM underscore G. Oh, I forgot. A simple underscore. It's amazing how code will break because you forget something. Okay, there you go. So now we have to set your duty cycle. So the way you set duty cycle here, it's with the period width. Okay, so the API function call for that is going to be PWM pulse width set, right? So I'm trying to go for 50%. So because half of 10 million is 5 million ticks, so that's what I'll choose. And again, this API function call will also take in your base value and then the output pin and then the tick value. Okay. So since we have 3 pins here, we're gonna have to write it 3 times. PWM1 underscore base, PWM underscore out because it's an output pin. We chose 5 because that's PF1. And 5 minutes, 5, 50, 100,000, 50,000, 500,000. So I count this every time because that's one of my weaknesses in life. I cannot see the amount of zeros indeterminate. So just that's how you think. And Control C. Oh, whoops, that's not what I wanted to do. Okay, here. Then now we change this to 6 here. Okay. And let me make sure everything is okay. Everything is okay. Cool. And this is 7. So they should all be 50%. I have gone and configured the width for all of the pins, but I think I'll just use 5 and then we'll go to 6 and 7. Okay. So now after we do all of that, we have to now enable PWM module. So when you do this with a register, you would first actually disable the PWM just because you don't want some of the values to load in first, right? So you clear it and then you disable the generator. Then you plug in your values and then you have to enable them. For the API version, you don't really have to disable, it just disables by itself. So enable PWM module, right? You go PWM gen enable PWM1 underscore base gen underscore 2. So this enables the second generator of base 1, and this one enable. And now I'm going to enable the third generator. Okay. Oh, okay. What the heck? Well, my cursor changed. That's funny. Hey Matthew, do you know how to reverse this? Do you know how to reverse the black cursor? Because it will now it's gonna delete the one before. Insert button.
So you may have to function insert to turn off
Okay, where is insert button?
control insert. It should be top right of your keyboard.
Yeah, I don't have that actually.
You do.
Well, that's fine. We'll figure this out. We'll just go on with it. Life moves on. So now basically my cursor has become the one similar to the one in command prompt and not the code composer version. Yeah, you see that? There you go. That's the difference. In any case. Okay. So we have enabled them. This is an API call to enable the PWM module generators. Done so here because the values of gens are satisfied. So you only want to do that when the required values for the generators are satisfied, right? Because if you do it beforehand, it will mess up in the actual board because again, the execution goes top to bottom. Now you have to do something interesting here. Even though we have configured the pins, we have not actually allowed the pins to have the values that we want, right? And the API call to do that is PWM out. PWM out. Output state. So in this API function, it takes base and all the pins. So now you can actually include all of the pins at once. What I'm gonna do is I'm not gonna do that because it's for the examples. I'll use one by one as I go. But first, let's do the first one first. By first one, I mean pin 5. Okay, and then parentheses. You don't need a parentheses here. You can. I have it because I had like 3 things. I just like doing it just so that I know what the pin is. PWM out _5 _ bit. So the bit is because it's a bit, goes by bit. And true, right? So this true basically says, hey, okay, is the processor allowed to output a value with PWM? If you put it false, which I'll show you, it will not work. And so before the actual lecture here started, I had a blue LED that was blinking here. I actually made it false. That's what stopped. So we'll do that now. It works, so we're good. And actually, we're okay to start seeing what it does. So I'm gonna write an infinite loop here with nothing inside. And this is no longer required. That's not okay. This is no longer required because it's an infinite loop. So let me build it. So the reason I'm putting this infinite loop is just trying to show you that the modulation, because what will happen is it'll keep on being here and the program will just never end. Okay, so let me upload it to the board. Can they still see the TIVA-C, by the way?
Yeah, we can see it.
Okay, cool. So let me reset. You see the blinking here?
You see the blinking.
Okay, yeah, but I'll just have to come back here to make more changes. Okay, there you go. That's the actual modulation with the 1.25 megahertz clock tick with the 10 million ticks divided in half by 5 million. So it's supposed to be 50%. I would take my word for it because there was one of the things I did have trouble with sort of verifying if it was sort of true or not, just because the text to second translation is sort of difficult. But yeah, it is 50%. I think from here, what can I go back in the code? Post mode? Yeah.
You gotta start sharing.
Okay, cool. I'll go back to sharing the TIVA-C code here. What I'll do is I'll try to simulate something that will that's similar to your brightness going up and down. And so now I have to actually declare a new variable here because I'm going to be using that unit. 32 underscore T, I believe. Let me double check. Check that value. Yep, it is correct. Okay. WIDTH. So that's the width. The reason I have this is because, again, as I explained, all of these values only takes in unit 32. So I need it to be that way. And inside here, I'm going to write a for loop. Two for loops. Or 0 width, as long as the width is less than 10 million value, which is the full cycle here. Because it can't be more than that, which doesn't make sense logically. And if it's less, so PWM, and I'll just get pros with set here, this value. And right now I'm only talking to port 5, so that's why it's red. We will be changing colors eventually. Here, you just want to write with. Right. Okay. Now another for that will put a delay, actually system delay. So this function here is a system control delay. This is an inbuilt function, well, not inbuilt, but like an API function call that delays the clock by a certain amount of tick. And that function also is in this library. Basically anything with system control, it's in that library. Each one has a special library. And I have the delay here is also 10 million, supposed to be a second really. I don't think it's fully accurate like the Google thing that I saw, but again, I didn't really open the article. I just Googled how many ticks in a second, and the first thing I shared was 10 million. So I was like, I took the word for that. Okay, so we delay it here, and now, so this one, what this one will do is it will go from 0 to high essentially, and then on the bottom one now it'll go from high to 0. Okay, so that's why I'm starting with width equals 10. I spelled it wrong. Look at that. Yeah. See, it sucks when you don't have the red on the line here. Usually I'm writing essays, it tells me that I'm spelling wrong, but not in code. Okay, so as long as width is greater than 0. So once upon a time when I took math for the first time, I couldn't write these for loops, and that was a struggle. And now I'm gonna be right. So that's progress. Okay, so same thing. Now this one will go from high to low. Just copy it. And we'll delay it again so that you can sort of see it. Okay. Right. You have to stop this because this, so like whenever it's on pause or like play mode, you have to sort of stop it because it's trying to refresh and not too sure. So it's just a code composer thing. Again, more errors. Let's see. Width isn't defined, so I'm spelling width wrong for yeah, I'm just gonna copy paste this. I probably spelling it wrong. Look at that.
No, you spelled the definition.
Really?
It's WIDTH. So you look at line 66. Read line 66.
Uh-huh.
Did you get WIDTH?
I spelled this wrong. It's only wrong if so it's not wrong in terms of grammar spelling. It's wrong because it doesn't match the same characters as a definition. So that's why I like code. You can spell wrong things as long as you make it look the same. You're good. So that's what I'm trying to do. Yeah, well, I'm not teaching English here. And in my defense, English is my second language. So yeah. Okay. I'm pretty sure there's a faster way of doing this, but oh. Okay. Usually you do want to have the right spelling. actual right spelling, just so whoever reads
You
it.
forgot one. 72.
Right, yes.
Hello there.
Anyways.
When did you become a PE teacher, Matt?
Yeah, the thing is, if I hit space, it's gonna delete a character. Which one?
How they call it?
72.
Right.
Next to the 4.
Oh, this one you mean?
Paragraph.
Oh, okay. Okay, should work now. It works. You should spell your words right. This issue wouldn't happen. Trust me, this happened to me at home. So when I was like, I just can't. With is one of those spellings that I cannot spell right for some reason. It just you see that TIVA stop blinking. So okay, I have to stop share. Okay, reset that, and you can see it blinks faster. I wish you could see it better, but you see how it stays there. Now it's at high, and now it'll start going smaller. Basic, and then it will. Okay, there you go. It shows the delays are pretty slow, so you can't see, but that's kind of how your intensity is going up and down. It is like blinking, except you're not quite blinking at the same rate. So now let me go back to sharing mode. Yeah, I'm gonna show them that that one line that I said about true or false. It matters. So right here, earlier I had said like you had to put this true, right? So if you make it false now, it will no longer work. Like that blinking will stop. Let me set this. Okay. Now let me up. Oh, okay. It was just I was trying to upload the code. You change the screen.
I mean,
It's
upload it, right?
yeah, it's fine. So you see how now it doesn't work anymore. So like you have like the actual PWM, right, is actually happening inside. You just can't see it because there's no signal coming out. You have blocked it. So you do have to have it true. Right, yeah, it's fine. Can you okay. Let me share. So now I'm gonna try to alternate colors. The only sad thing here is that I don't actually get to make new colors here. I can only combine red, green, red RGB, but like I don't think I can control the percentage, or at least I don't know how from right now. So what I'll try to do is I'll try to make outputs true and false depending on where I am inside the while loop, right? So here, I'm going to delete this. And before I mess it up, I'll just copy this. Okay. Yeah. And you'd also want to basically have this line 64 inside the while loop so that you can close and on it, and you can turn it on and off inside. Because if you do it outside, it will also start writing values to the pen, and then it will mess up, right? So you want to do it inside here. We delete this. So what I'm doing here is actually not online yet. F1. Okay. I'll just write the for loop here. Equals to 0. With less than 1, 10, 100,000. With set underscore base. Okay. Yes. In hindsight, I should not have deleted some of this code, but that's fine. CTL delay. 100,000. All right, I think I put a delay of 100 million ticks here, so just so that it's just longer. Okay, so the thing with the black tick, well, I think it changed. Oh, never mind, it did not change. The black curse, it's gonna mess up a few things here. 10, 100,000, 100,000, right? Yeah, do you know how to fix it?
No, I don't. I was trying to see what you're searching. I haven't.
Yeah, I thought I was like,
You know, I didn't think you would. I thought it was
I was like, I genuinely just don't see it. I was like, well, where is this? Yeah, I know it's
strange.
yeah, it's just weird.
Hmm.
What is that? Also, you gotta be mindful of your braces here because it could just be in the wrong spot, wrong time. It looks like there you go. Now let me so this everything here is similar to what I did earlier with the red, and there's more errors. Hold on, let me double check this real quick. I messed up the width again, bro. Where? Oh Lord.
You spelled the middle one wrong.
Oh yeah, I spelled the middle one correctly. That's what happened.
Slash.
Yeah. All right, hold on. Okay. So that's correct. This is for your red. Let me cap it. There you go. Okay, so now I'm actually gonna now turn off port 5. Oh. False. Okay. And in here now we'll turn on the second one. PF out 6-bit. Go true. PF2. All right, so now PF2 is on. So now this one will blink blue. And I can pretty much copy this code from the top. What is this? Why do I have an extra freaking what the? Wait. Oh. Okay, this is for that. This is for this. Where is this? Oh, no, I can't. My apologies. For the main function, this is for the while loop. So you have to be mindful of those. Those things will always creep up for no reason. Actually, we want to do it here. Okay. So in here, all I have to do is change up. All I have to do is change 6. What the 6? Oh my. Okay, out 6 here. Okay. Let me double check this if this is correct. Cool, that's correct. Now I'm gonna turn this one off so that we can have green. Okay. False. You're right. Okay, so now we have to turn on the last one. Just take a picture, that's why. Okay, now we turn this on, and then same sort of thing follows where the width value, except now I have to change it to 7 here. Okay, 7. All right, cool. And then now I also have to turn this off. So if you don't turn this off, what happens is the colors will mix. I think red and blue makes brown. I may be wrong. I may be wrong. It makes purple. There we go. So you can actually make purple. Actually, we'll make it purple. How about that? No, we don't want to do that because then it's actually, you know what? We'll do it because we'll not close the green because this one is green, right? We'll just not turn off the green. So what will happen is it'll go red off, blue off, green. Red and green will mix, and blue and green will mix. And then green will stay by itself, and you'll just, I think. If not, we'll see what happens. All right, cool. Let's just try it until let's see what's wrong here now. 109. Oh, what is this? I think so. I'm just trying to see what that is. It's wrong, but I'm not. Let me see. Hold on, because that with. I think it was that. I thought this one was for the width. Oh, let me try. Yeah, no, I think it's too much brackets. Yeah.
Damn, one bracket.
All right, let me download the code here. So if it works, I hope it works.
Very potato color.
And all of this work really at the end of the day, just to see the modulations.
Which slide are we looking at?
The TIVA-C one.
There's 2.
Yeah, so now the delay is a little bit longer because I think I made it 100 million, so it stays there for a while. Whoa, okay. I guess the code didn't work. Or it doesn't move. I'm not sure, one or the other. Okay.
It's not mixing the colors.
It's not, so we have to figure out why it's not mixing colors. We'll see. I didn't do this, so like this little part is the one I just made up right now. So I've not figured it out correctly. Let me see. It should be at the very least, if you just go by the execution, it should be turning it off. It's not turning it on. That's the okay. Oh, it just turned off. So wait, I think it might just be the delay. Oh, well. Actually, it does. It's just the delay is so long. I have to, yeah, I have a delay of 10 minutes. Okay, it's a
So we're
delay.
basically waiting like 2 minutes for each of the colors to change.
Basically the time. All right.
Just explain again what's going on.
Oh, so now this is talking to a different port pin inside port F, right? So this is talking to pin 6. So it's PF6 on the actual port. So if we were to put a female Y here for PF6 or even a male Y underneath, and then plug it into a breadboard, you'll have a signal going through. So if you want to see that oscillation happening in an oscilloscope, that's how you would do it. You would just plug it in, plug to your breadboard, just have that connected to your oscilloscope. Make sure you have the ground connected, and then you'll see the modulation. So this will also turn to green. You just, the delay is pretty long. And the value inside of it, calculating is pretty high too. So, because after a certain point for the eye, it looks like it's just bright, but it has to go all the way to 10 million ticks and then 10 million down. So now it's stopping.
Now it's stop.
It stops for about 100 million ticks. Just because I thought that would be enough to see something clean.
So
you gotta
just
cut everything in half.
No, I mean, it's fine.
just change the delay.
Yeah, just change the the delays and just even the take values. You'll be
So
fine.
now it's green or red? Oh, it's red.
It's red now. So, okay, green didn't happen.
Interesting.
Wait, why did green? Yeah, as far as it, because see, like,
That's okay.
yeah,
We'll fix it, update it on your end, and then switch on.
yeah, I think we're done for the today though.
Just say we're done.
Yeah, we're done. Thank you for coming. Thanks, Justin, for watching the basically a lecture here. But